Welcome to lesson 8.7, 8, 9, and 10. Today we're going to continue to talk about bonds and we're going to calculate some bond energies that occur in when in a reaction. Okay? All right. Again, bonds are forces that cause a group of atoms to behave as a unit. They result from the tendency of a system to seek its lowest possible energy. Now, the bond concept is actually a human invention because there's no line that exists between atoms. The atoms just have an electron density between them. So the bond concept is a method for dividing up the energy evolved when a stable molecule is formed from its component atoms. So we use models to look at these things, and in these models, when we look at the electron density, we may see something most of the time we see something called a single bond where one pair of electrons is shared. But when we get into some of the other chemistry, especially carbon chemistry, you'll see double bonds and triple bonds. Now, this table shows the different bond energies. Notice that as you go over to multiple bonds, the bonds become stronger. So if you look on that table for a carbon-carbon bond, it's right here. Carbon-carbon bond is 347 kilojoules, where a carbon-carbon double bond is 614 and a carbon-carbon triple bond is 834. So as more electron density occurs between the atoms, then we have a stronger energy to pull them apart. Okay, so when you look at enthalpy change, you look at the bonds broken versus the bonds formed, and that's what this energy that is between these bonds is called. It's called enthalpy. So bonds broken minus bonds formed. And so what we're going to do is that equation looks complicated, but we're going to walk through that in terms of this next problem. And so what I might do here is I might take that particular diagram and move it down here so that I can work that problem with that on the same page. Okay, so let's look at this this particular. So the bonds broken minus the bonds formed, and so let's look at this. So the bonds broken are going to be on this side, and the bonds formed are going to be over here. So what we have to know what these molecules look like. And this lesson kind of jumps ahead because in the next particular lesson you'll learn to draw Lewis structures, and so you kind of need to know how to draw what the Lewis structures look like. So in this first example, this is methane. And so that first molecule right there is methane. And so how many carbon-hydrogen bonds do we have? We have 4. So we have 4 carbon-hydrogen bonds that we're going to have to break. The chlorine is going to form 1 chlorine-chlorine bond. But because we have a 2 in front of this, we're going to have 2 of those total. Okay, so here we had 4 carbon-hydrogen bonds. We didn't need to multiply it by anything because there was a 1 in front of there. This, we have 1 chlorine-chlorine bond, but we need to multiply it times 2 because there's 2 there. And the same thing with fluorine-fluorine. So there's 2 bonds there. Now over here, this molecule is going to be very similar to this one here, except it has 2 carbon-fluorine bonds and 2 carbon-chlorine bonds. The next one, there's an HF bond there, and there's 2 because there's a 2 in front of it. And then the last one is an HCl, and there's a 2 because there's a 2 in front of it. All right, so what we're going to do is we're going to do the math. We're going to go down to this table and figure out what's going on here. So CH bond is 413. So we're going to have to take, so of the broken bonds, we have 4 times 413. We have 2 chlorine-chlorine bonds, and chlorine is 239. And then we have 2 fluorine bonds, and fluorine is 154. So the bonds made, we have 2 carbon fluorine, so that's 2 times 485, 2 carbon chlorine, 339, 2 hydrogen fluorine, which is 565, and then 2 hydrogen chlorine, which is 427. And so it's going to be bonds broken minus bonds made. And let's see, let's pull up a calculator. One 652. 2 times 239 would be 458, and then 2 times 154 would be 308. So the bonds broken is 2,418. And then down here, the bonds formed, so 970, 678, 1,130, and let's see, 854. 12, so 15, 23, 11, 17, 18, 26. So 2, 4, 1, 8 minus 3632, and that's going to give us a negative kilojoules per mole. Okay. All right, so I won't bore you with that calculation, although I could pull it up on the calculator here. So 2418 minus 3632, and we get negative 1,214 kilojoules. So that's how much we get out of that reaction. How much energy leaves the reaction. What I'm going to do here is I'm going to pull up the completed notes on this. And oh, I must have done my math incorrectly. So I got negative 1,194 kilojoules per mole. Calculated something incorrectly. It looks like it was over here on this side. And then the next problem, given the average bond energies, calculate delta H. So same kind of thing here on the left-hand side of the equation. I have an HH and an FF, and so there's a 2 there, but that 2 just indicates that there's 2 H's and then 2 F's. Over here, I have 2 HF, so I have an HF bond, but I need to take that times 2 to get what I need there. Okay. All right. I hope that wasn't too confusing. Utilize your textbook if you need to. Before we move into the next section, which is the VSEPR theory, the localized electron model means that we have when we draw the molecule of a compound, then we can have what we call lone pairs and bonding pairs. So some atoms will have electrons that they don't share with other atoms in the compound, and so those are lone pairs. Now what a lone pair does is a lone pair occupies more space. It has more repulsion than a bonding pair. And so that's why you'll see as we go through the VSEPR structures why the molecules have the three-dimensional shape that they do. All right, well that completes lessons 7, 8, 9, and 10.